Hi. So everything is a token. One architecture, every domain. Same attention, same feed-forward network, just different tokens. And we will, of course, talk a lot about text in the last week when we talk about large language models. But since then, transformers have been applied to actions, to robotics, to vision, to speech, to biology, and more. And I want to quickly show you, what we are doing with all these different domains. So this is an encoder only architecture. So this is a transformer encoder. And what people did were so this is a paper from Google, and they basically patchified the image. They converted the image into patches. And what they then did to these patches were they would take the patch and then flatten it, and then use a linear layer, project it, add those positional encodings, and then essentially have your encoder give us a vector, which you can then again put it into an MLP head, linear classifier, and then you can, for example, do classification. You can do regression. You can do any of the tasks. So essentially your image then gets represented by this vector through a transformer encoder, and this is the state of the art. This is way better than the CNNs, but it's just that it needs a lot more data. If you train it with just ImageNet, CNNs is still better, but if you give it a lot more data, which we have access to, transformers do better. In modern methods, I'll talk more about it when we talk about the VAE next week, variational autoencoder, but instead of doing it directly on the image, so the VAE looks a little bit like a unit, like an hourglass, and then we do this business, this so-called patchifying business. So the function called is patchify, and we do this to the, to the latent space, of the VAE, of the encoder of the VAE. So, but the idea is same, and even for images, transformers is the state of the art. Same for audio. Audio, all you want to do is you can, take, let's say, this spectrogram. So this is the input spectrogram. You see, the different energies in this spectrogram. You would patch split it with overlap, and then you would basically just do the similar thing that we were doing earlier. You would do a linear projection, you would add these positional encodings, and then you would put it into the encoder, and then outside the encoder you have your final linear block, which will then give you the output. So here the paper says the proposed audio spectrogram transformer AST architecture. The 2D audio spectrogram is split into a sequence of 16 cross 16 patches with overlap, and then linearly projected to a sequence of 1D patch embeddings. Remember, a transformer encoder or decoder can only work with 1D because it works with sequences, right? So we need to convert it into a 1D one way or the other, and we do it using a linear projection. Each patch embedding is added with a learnable positional embedding, and an additional classification token is prepared to the sequence, prepended to the sequence. The output embedding is input to a transformer, and the output of the class specific token is used for classifying the linear layer. Exactly same how we did for vision. By the way, there's a lot of similarity between vision and speech. Here we literally represent the speech as an image, as vision. But again, speech is just, is continuous, is 1D. Images are also continuous, but 2D. This is something very, very new, has been causing a lot of wave in social media. This is Personaplex, and this is essentially a speech-to-speech model by NVIDIA. Came out this year. It's like from January this year, and what we're doing here is, again, so what does it mean, a full duplex model? A full duplex model is when the model is listening to you while speaking, like what we humans do. Earlier, we would use a cascade of, let's say, a speech to text, ASR, so a speech to text, and then a text to text, and then a text to speech. And then we would use something as a voice detection, so a VAD score to know if the person is still speaking or not. But all that is the bygone era. What we now do is we kind of have this agent audio, and we have, you know, the user audio and the agent text all kind of coming into, you know, the depth transformer, and then there's also the temporal transformer, and this then kind of gives you the output, right? So this is essentially the input, and it's an autoregressive output, and it's built on a paper called Mochi, so MOCHI, and it does very well, and we are actively working on it. And if you're interested in speech, I highly recommend you check it out. Similarly with AlphaFold. So we recently had Pratik, a PhD student at UC Santa Cruz, come and give us a talk on how AlphaFold works. But essentially the Evo former here is like this big giant transformer. So even to predict the structure of proteins from the input amino acid sequences, it's a transformer. So is with robotics. So here we have the VIT. VIT, if you remember, is the first transformer I talked about today, the encoder-only architecture, where we patchify the image and then put it into the VIT. And what these guys are doing here, and this is like a tutorial, I highly recommend you check this out on the Learn OpenCV blog, where they use, you know, a language model to then we also then have, you know, the vision tokens, and then finally after the vision tokens we have the action tokens, and they are now called VLAs, vision language action model. One of the newest ones is something called as AlpaMeo, again from NVIDIA. So AlpaMeo is agent, is a model, is a VLA for autonomous driving, and I recommend you check it out if you're interested. And actually Jensen Huang announced this in CES this year in 2026. And then what you can do is you can have essentially, you know, your output of your action as, you know, this, which you can detokenize. So these are tokens, and each token has a meaning, and the meaning of the token is essentially, you know, delta T and delta R. Delta T stands for delta translation, delta R for delta rotation, and then the robot can actually take action. So for example, here you see that they're saying the prompt is given image instruction, bring me a drink, and then it plans it in text, plan 7-up can, and then this is the action, and this action can then get translated into those delta T's and delta R's, and then finally also a grip action, right? And if you see, this basically is the language input. What should you do, the robot do? It then comes up with a text plan, and then finally the action tokens, right? So even robotics is just transformers. And the message here essentially is that, you know, everything is a transformer. You just need to know how to convert it into a token. One of the issues with transformers is, or not issues, let's say one of the design aspects of a transformer is that it works with discrete tokens. So whatever you get, you need to learn how to kind of discretize it in tokens, and you do it using just patchification. You can have a learned tokenizer the way we do it in LLMs, which we will learn in the last week, and so on. But everything is a transformer, but we have to learn all this that we did in the last weeks to build till here. And going forward, unless, you know, if you're working on big large scale projects, most likely you would be only touching transformers. But then there are some very specific niche problems where you would still maybe use a CNN. And always start simple, right? If a rule based algorithm can do it, never think about a transformer. And then if a linear transform can do it, if a logistical regression can do it, if an XGBoost can do it, please, let's just use those instead of trying to train these heavy transformers. And that's all that we have for this week. Thank you.